So let us take a look at the concept of least squares. Okay, so more precisely, the least square principle for regression. So we have values of x and y. Okay, we have the values of x and y, and for different values of x we have different values of y, and let's say we plot it in this graph here. We plot it in this graph over here. Okay, and this is what the points look like. So what we notice is that generally we see that these points are moving up. Okay, these are moving up. So which means that if there were more values of x and y, the points will lie in this direction. You will be moving up. Okay, so for these values of x and y, these are the points. If we had more values, of x and y, those points will continue to lie in the upward direction. So that is why we try to draw a straight line, or we are predicting or expecting that the values will lie in the upward direction. So that line can be represented by this equation, y is equal to a plus bx, where a represents the y-intercept and b is the slope. Y-intercept is nothing but the distance between the origin and this point here where the line meets the y-axis. So this is called the intercept. Another way of defining intercept is the value of y when x is equal to 0. And b is nothing but the slope. It tells us how much y value changes when x value changes by 1. So we see here that this line, which shows the expected values, can be drawn in different ways. It can either look like this or this way, or like these two other lines. Now what we can also say is that as the shape of the line changes, the values of a and b also keeps on changing. Or we can also say that the value of a and b will determine the shape of the line, because if the y-intercept was this much and the slope was this much, the line would look like this. And if the a or the y-intercept was this much and the slope was this much, the line would look like this. So we have different shapes of the line depending upon the values of a and b. So this line, okay, the straight line, will represent the expected values, and these red dots or red points represent the actual values. Here we introduce another concept, which are called deviations or residuals. And deviations or residuals are nothing but the difference between the actual value, the actual values minus the expected values. So if we look here, depending upon the different shape, so this distance, or this difference, this is a deviation or a residual. Let us denote this by d1. Let us call this as d2, and let us take another deviation, this distance, because here we have expected values of y and here we have actual values of y given a value of x. So that is called a residual or a deviation. So if we look here, by changing the shape of the line, the deviations also change. So if we look here, for this point here, for this value of x, okay, so let us take this point. Now this point is also represented here. Now if this line looked like this, there's a deviation, right? But if this line looked like this, there's no deviation. The actual value is equal to the expected value. And if the line looked like this, for this same point here, if we draw another line, now we have a deviation. from the actual value and the expected value. So how can we draw a line so that we reduce these deviations? And this, if we draw a line which passes through the points in such a way that the deviations are reduced, we get the line of best fit. And the line of best fit will help us give the most exact value of y given the value of x. And like we've said before, the shape of the line will depend upon the values of the y-intercept and the slope. So that is where we have the least squares principle for drawing these lines, which we will later call the regression line. So the least square principle tells us that in order to obtain the line of best fit, the sum of the squares of deviation should be minimum. In other words, deviations, the sum of the squares of deviations, which means if we add up all these deviations, they should be minimum. Okay, so let us take for example this. So this is one deviation, let us call that as d1. This is another deviation, call that as d2. Another deviation from the line, d3. This has no deviation, it coincides. So this is another deviation here, let's call d4. A small deviation here called d5. This is another deviation, d6. Another deviation, d7. And another deviation, d8. So if we add all of these, okay, add all of these deviations, we have d1, d2 up till d8, they should be minimum. Okay, and like I've said before, the shape of the line will depend on the value of the y-intercept and the slope. So that is why it all depends on the values of a and b, because by moving these values, the shape of the line also changes, and when the shape of the line changes, the deviations also change. So if values of a and b are obtained, then the line can be determined. So to define a and b, we have the following normal equations, and they satisfy the least squares principle. Okay, and how we've obtained these equations, we won't show that, but by solving these equations, we get the values of a and b, okay, or the value of the y-intercept and the slope, and based on these values we get the equation of the line of best fit. And if suppose we want x to be the dependent variable, suppose we want it to look in this way, okay, same principle, same idea, only the normal equations will look a little bit different. So in this case we have something like this: exy equal to a ey plus b ey square. So you solving these normal equations, you get the values of a and b, the intercept and the slope, which gives us the line of best fit. And the line of best fit is when the difference between the actual values, the sum of the squares of deviations will be minimum. So, and like I've explained before, the deviations are nothing but the difference between the expected values and the actual values. So that is how we fit a regression line or equations based on the least squares principle.